Hey everyone, and welcome to a masterclass on one of the toughest puzzles in engineering, system integration. Today, we're going to break down how you actually bolt a super high-voltage electric system onto a hybrid cement mixer. You know, that place where raw mechanical force, powerful electronics, and really complex software all have to learn to play nice together.
You know, this quote right here, it's pretty much the heart of everything we're talking about today. It's a fundamental truth. Doesn't matter if you're building a rocket ship or, well, a truck. Anytime you have two complex systems meeting, you create this gray area, this interface. And if that interface isn't perfectly, absolutely defined, that's where things go wrong. But this isn't about what can go wrong. Nope. This is the story of how engineers get it right. It's all about the incredibly rigorous, methodical process they use to completely erase those dangerous gray areas. It's about making sure that every single wire, every signal, every decision has a clear owner who is absolutely accountable.
All right, so here's the game plan. We're going to start with the core philosophy. Then we'll define the 5 critical boundaries you need to know about. After that, we'll get into the weeds of the mechanical and electrical challenges. And then finally, we'll see how it all gets proven out in the real world through validation. This is the blueprint.
Okay, so first things first. The absolute #1 principle of system integration is creating a common language. The goal here is to get the company that builds the truck chassis, the OEM, and the company that builds the mixer, the TEM, to agree on every single point where their systems touch, and to do it before a single piece of hardware gets built. And look, this isn't a nice-to-have. It's totally non-negotiable.
Right, so how do you actually get rid of those dangerous gray areas? Simple. You draw really clear lines in the sand. When it comes to putting a vehicle together, this means defining 5 crystal-clear boundaries where the truck chassis essentially hands off responsibility to the mixer's superstructure.
And these are the big 5. You can almost think of them like the precise points where the two engineering teams have to come together and agree on everything. Each one is its own little world, physical, electrical, thermal, and each one needs its own unique set of rules to make sure the whole thing works safely and does what it's supposed to do.
All right, let's start with the easy one, the physical boundary. I mean, this is as literal as it gets. It's the top flat surface of the truck's frame rails. Simple rule, everything below that line belongs to the chassis team. Everything above it belongs to the mixer team. It sounds basic, but it's the foundation for everything else.
Okay, next up, high voltage. The chassis provides one single heavy-duty 400-volt socket. Just picture a wall outlet in your house, but, a whole lot more powerful. The chassis team is responsible for making sure safe, stable power gets to that socket. But the second the mixer plugs in, the responsibility for using that power safely is shared across the entire system.
Then you've got the low voltage side of things. This is the 24-volt bodybuilder connector. This is basically the brain of the whole operation, the nerve center. It doesn't have the muscle to move the mixer, but it powers all the controllers, the sensors, and the communication network, all the smarts.
And that, of course, leads us to the digital border. You absolutely cannot just plug the mixer's computer into the truck's main network. I mean, can you imagine? That would be a total disaster for safety and security. So instead, you create this communication boundary, a dedicated gateway that's basically a digital firewall. It translates messages and makes sure the mixer's software can never, ever mess with critical truck functions, like the brakes or steering.
And last but not least, we've got the thermal boundary. That big electric motor, it generates a ton of waste heat. We're talking about 8 kilowatts. To put that in perspective, that's enough to power a few ovens in your kitchen, all at once. So this boundary defines exactly how all that heat gets pulled away safely so nothing overheats.
All right, let's dig into the first huge challenge here, mechanical integration. This is a classic conflict in engineering. It's really a battle between a system that's designed to flex and twist and another system that absolutely must stay perfectly stiff and rigid. So here's the fundamental problem. A heavy truck chassis is built to twist. That's a feature, not a bug. When it's driving over some rough construction site, that flex is what keeps all the wheels on the ground. But the mixer body? It's carrying tons of concrete. It's built like a tank. It cannot twist. You see where this is going, right? If you just rigidly bolt them together, something's got to give, and it will break.
The solution, though, it's actually pretty brilliant in its simplicity. Engineers use 2 totally different kinds of mounts. Up at the front, they use flexible mounts with springs that let the truck frame twist all at once. But in the back, they use rigid shear plates to lock the frames together. That's what transfers all the massive forces from accelerating and braking. It's really the best of both worlds.
Okay, so we're leaving the world of steel and bolts and moving into the invisible stuff, electricity and data. But the rules here, they are just as, if not more, absolute.
Okay, I want you to meet the single most important safety system of all, the high voltage interlock, or HVIL for short. It's a low voltage circuit, kind of like a lifeline, that snakes its way through every single high voltage part in a big daisy chain. If anyone opens a service cover or unplugs a connector, that chain is broken and the main high voltage power is shut off in less than 200 milliseconds, literally in the blink of an eye.
And this is where it all comes together. You can see how a few simple, hard numbers create this entire web of safety. That grounding resistance, it has to be under 10 milliohms. That's what stops you from getting electrocuted. Those big orange cables, you have to secure them every 300 millimeters to stop them from vibrating and shorting out. Even the bend radius is critical to protect the shielding inside the cable. Every rule is there to prevent a specific catastrophic failure.
So, let's get back to that digital firewall for a sec. The CAN gateway's job is basically to be a super strict translator. The mixer gets to ask for things like, hey, I could use some more power over here, but it never ever gets to command the truck's main systems directly. The gateway filters all those messages, makes sure they're safe, and only then passes them on. A direct connection, absolutely forbidden.
And this whole startup process, it's the perfect example of what we call a digital handshake. It's not as simple as just turning the key and hitting the gas. The truck has to check its safety circuits. Then it has to slowly pre-charge the mixer's electronics. Then it has to broadcast a signal saying, okay, power's on and stable. The mixer has to hear that and reply, got it, I'm ready. Only when every single one of those steps is confirmed, in exactly the right order, will the system let that powerful electric motor even think about starting.
Okay, so you've got all these clear boundaries, all these strict rules. But how do you actually prove it all works in the real world? Well, that brings us to the last and maybe the most important step, validation. You have to test before you trust. And that's the million-dollar question, right? Literally. You can't just build the first one and cross your fingers. Testing on a finished truck is insanely expensive. It's slow and it can be really dangerous if you're trying to find the breaking points. So how do you test for things you hope will never happen without breaking an incredibly expensive piece of machinery? The answer is you build an Iron Bird. It's a really cool idea they borrowed straight from the aerospace world. You take all the real hardware, the actual controllers, the real motors, the same wiring harnesses, and you lay it all out on a test bench in the lab, exactly how it would be on the truck. This lets engineers run the whole system, test every single function, and even intentionally create faults to see what happens, all in a safe lab environment before the first truck is even built. And in the end, after all that design and all that lab testing, it all boils down to this checklist. Every single truck that rolls off that assembly line has to pass this final, non-negotiable commissioning test. Technicians go back and retest these critical safety systems, measuring the exact disconnect times and resistance values to make sure every single vehicle is just as safe as the last. No ifs, ands, or buts. No exceptions.
So when you really get down to it, conquering that interface is everything. By defining clear boundaries, setting up strict rules, and then testing everything relentlessly, engineers can make two incredibly complex systems work together like they were always meant to be one. And that kind of leaves us with one big question to think about. If this is the level of detail it takes for a cement mixer, just imagine the mind-boggling complexity ahead for things like self-driving trucks, electric ships, and fully automated construction sites. The interface, that's where the real challenge is, but it's also where all the incredible innovation is going to happen.